boundary value problems or the shooting method. Solution. So what we started with was initial value problems, where even if it was a second order differential equation and you wrote it as two first orders, where one of the unknowns was the first derivative, you would know the initial value of that. You'd know the initial value of that v, say. It might be the initial velocity. A different scenario is where you have information not all at the start, but at multiple points. So the difference between them, the textbook answer here is both of them are differential equations. So the difference is for an initial value problem, information is given about the solution at a single point. So for example, just something where you know the initial displacement and velocity, for example, you could just write down maybe a spring. So mass times second derivative of displacement, in other words, mass times acceleration is equal to the spring force, where you're given maybe the initial displacement is 1 and the initial velocity is 0. And the point being, you're given information about the solution at a single point. Whereas for a boundary value problem, information is given about the solution, about the solution more than 1 point. So for example, a typical example, even though it's not really what I'm looking for here, would be your plate, your equilibrium temperature at a plate, where you know the temperature all on the boundaries, is given by the solution at multiple points, I guess. And the two kind of examples here you had was the temperature of a rod uninsulated, or you could do the bending moment one. So I'll do the bending moment one. For example, the second derivative of moment is minus load per unit length. That could be different things, and you're told, or you know, if it's simply supported, that the moment at 0 is 0, and the moment at, say, the span of the beam, let's say here is 6, is equal to 0. So you're told things not at a single point but at multiple points. So that's the difference between those. That's a question, fairly textbook answer. So we continue. So this question is more of an exercise, because if you actually look what it's asking to do, write it as two first order ordinary differential equations, and that's such an important skill. If you cannot do that, you are going to probably get zeros on things in your VBA assessment and your final written assessment. And then it's actually done the shots for us. So we're just using this formula. So it's just an exercise in that sense. So always the way, if you want to write two or second order with a second derivative as two first orders, you introduce a new variable, which you don't always have to, but you can call v, and it's the first derivative. So you're saying let dt dx equal to v. Now if you go from here and just kind of write down the answer, I'm happy. So what do I mean by that? So you have dt dx is equal to v, and if you're kind of happy in your head that the second derivative of temperature is the so the second derivative of temperature is the derivative of the first derivative, and the first derivative is v, so that's dv dx. Now I probably advocate working it out more carefully, but we'll just run with this anyway. This, in my opinion, is a bit quick. Like, where does that come from? Strictly speaking, that, well, we haven't answered the question because it wants So it didn't actually ask for initial value problems, but I would say that really you should be putting it as an initial value problem. So this is the differential equation for t. So put the initial value of t, which is 50. And here you'll note you don't know the initial value of v. So the initial value of v is unknown. So the bit of working out that you don't have to include, well, I think you should include it, to be honest. I'm going to include it in the solution actually. Although if you have the things with the bracket there, you will get full marks. You will have answered the question. I think more reliable is to do this. So we're going to differentiate both sides of this with respect to x. The derivative of the first derivative is the second derivative. And the derivative of v is dv dx. And therefore what you can do is you can write the differential equation 1.48 in terms of v's. So you would get dv dx plus 0.2 times 10 minus temperature equal to 0, and it's an easy job of just taking away 0.2 times 10 minus t from both sides to get what we have below. So this is saying, suppose you take these shots with a slope of 10, you're trying to hit 100 an overshot, a slope of 0 gives an undershot, find what the correct slope is. Just for argument's sake, I might just write down what I probably would have taken to be the first slope. Now I did write this question, but anyway. So x is going from 0 to 8, and the temperature is going from 50 to 100. So in my head, a reasonable first shot would be to shoot straight at it, and what you do in that case is rise over run. And the rise is 50 and the run is 8, and I think 50 over 8, maybe it's something like 6.2, it's gone, 50 divided by 8, 6.25, should trust myself. So I would have considered 6.25 to be a good first shot. But anyway, this question isn't about that. It's given some other shots. So someone just tried 10 and got 121.2, and basically just using this formula. So it's just training in the use of this formula. So the V0 that you should shoot with to hit, what are we trying to hit? 100 is VA, the first slope, which was 10, plus now the y of xf is the final y value that you're trying to hit. That's 100 minus YA, your first shot, 121.2, divided by YB, your second shot, 92.3, minus 121.2, that second shot, divided by VB minus VA, 0 minus 10, and presumably that answer is correct, 2.664. Okay, so that's that. So this question is very similar. I think I could have carefully gone through which questions to do. I think I might end up doing more than 4 hours and 10 minutes, so it'll be up to you to skip as such. Okay, so anyway, this is similar to the above. So again, to write something as two first orders, you introduce a new variable v, which is the first derivative, and in this context, v does mean something. It's the shear force. Now again, if you want to go from here to the answer and kind of do the next bit in your head, that's okay, but I think it's better to work it out carefully. So if I differentiate both sides with respect to x, I get that the second derivative of moment is the first derivative of v. And so that second derivative of moment in the equation 1.50 is in fact dv dx. So I think we're ready now to write down this thing. So our first equation is dm dx is equal to v, and our second equation is dv dx is the same as the second derivative of moment minus 10 e to the minus x squared. We put this asks for initial values. M of 0 is 0, v of 0 is unknown. Okay, so that's the first thing. And then again, there's two shots here. Now this v of 0 equals 0, you're trying to actually go, this v of 0 makes, this first shot makes more sense to me. So you're trying to go to 6. So at x equals 0, the moment is 0. At x equals 6, the moment is 0. So the obvious thing is to shoot straight at it with a slope of 0. This produces an undershot, and then going to slope of 10 gives an overshot. And now just to use this formula. So here the VAs and VBs aren't quite given, so this would be your first slope, and this would be what you hit. This is your second slope VB, and this is what you hit. And then the y of xf is the thing you're trying to hit, which is this 0. Okay. So this is question B. I get v of 0. I suppose it's a big V here, but it doesn't really matter. Is the first slope that we tried, which was 0. Of course, someone else tried. Y of xf is what we're trying to hit is 0. Minus ya, that's the minus 50.246, rounding to 5 significant figures, although I'm not going to recalculate. And then yb is 9.7543 minus the minus 50.246 times vb minus va. So vb is 10 minus 0, and I'm just going to assume that this answer here is correct, equal to 8.3743. So this is just an exercise, really. It's not really an exam question. So this is nearly a full question, but if you look at it, the hint, it says you just have to find v of 0. You can take your final shot to confirm your answer if this is not necessary. We will do that. Okay, so we're talking temperature against distance, and we are going from at 0 to 6, x equals 0 here, and we're going from 5 to 65. So our starting point is here, and our finishing point is up here. So, okay, the first thing we've got to do here, if we have a second order differential equation, is to write it as two first orders. And the first thing to do then is to introduce a new variable v, which is the first derivative. So let the first derivative be v, and we can differentiate both sides of this with respect to x to get the second derivative of temperature is dv dx. And that means we have, if we write the differential equation in terms of v, we've got dv dx plus 0.0280 minus t equal to 0, and just a bit of adding to both sides finishes that off. So we have this written as two first orders, and I recommend you do this. You don't have to. I mean, if you get the final answer, I'll be happy enough. But I recommend doing this for clarity for your Euler methods. So the first derivative is v, and the derivative of v is taking away 0.0280 minus t from both sides. This, I think it might make more sense actually to make that positive and then t minus 80, but we won't do that quite right here. Initial values, t of 0 is 5, v of 0 is unknown. So we'll come up with our first slope by shooting straight at it. You can do whatever you want, doesn't really matter, but this makes sense to me anyway. So it's 60 is the rise from 5 to 65, and the run is 6, so we're going to try an initial slope of 10. So this is our VA of 10. Now, there must be some kind of a step size. Yeah, there's step size of 1.5, so we might just draw a picture of the rod here. 6-meter rod. So step size 1.5 cuts it into 4 pieces. So I suppose this is x equal to 0, where the temperature is 5, and we have 1.5, 3, 4.5, and 6, where the temperature is 65, I think. And then we'll call this T1. This isn't strict. This actually just comes out of the Euler method, but we'll just throw it in there anyway. Okay, so we're going to do an Euler method. I just must set up my calculator. Okay, so we'll get going. So I'm not going to do too much by way of explaining here. Well, we'll do a little bit, I guess. So you know you're taking the initial temperature is 5, initial V is 10. That initial 10 is a guess. So there's no Euler method at that time. So you're looking first at what's happening at x equal 1.5. Then what happens at x equal to 3. Then what happens at x equal to 4.5. And then at x equal to 6, you're trying to hit with the temperature 65. But you probably won't, almost certainly won't get it. And there's two differential equations, so there's two Euler methods. So M1, what am I talking about? M1, temperature 1 is the previous temperature, which was 5, plus the step size, which is 1.5, times the previous V, which is 10. V1 is the previous V, which we've guessed to be 10, plus 1.5 times the previous slope, and the slope of V is minus 0.02, 80 minus temperature, and it should be previous slopes of previous temperature, which is 5. And this first number comes out to be 20, and this second number comes out to be, now I'm using Excel for a calculator, and I'm being a little bit lazy in the sense that I'm not doing the rounding exactly. So if you do the rounding properly, you might have slightly different answers. Okay, so that's T1. T2, so the next temperature, T2, is the previous temperature, which is 20, plus 1.5 times the previous slope, and the slope of T is V, that'll be 7.75. And the next V is the previous V, which was 7.75, plus 1.5 times previous slope. Slope of V is up the top of the page, minus 0.02, 80 minus temperature, previous slope, so previous temperature, which is 20. These numbers come out to be 31.625, and this V comes out as 5.95. Now we go to the next one. So the next temperature is the previous temperature, which is this 31.625, plus step size 1.5 times slope of temperature is V, 5.95. V3 is equal to previous V, which is 5.95, plus step size, which is 1.5 times previous slope, minus 0.02, 80 minus temperature, but it's previous temperature, which is 31.625. So this temperature comes out to be 40.55. Don't ask me about the rounding there. And this one comes out to be 4.4988. 4.4988. You don't need the final V. We're heading probably for an undershot here. We'll see what happens. So the final shot, T4, previous temperature 40.55, plus step size 1.5 times previous slope, slope of T is V, 4.4988. And I said the rounding is all over the shop here. We won't worry too much about it. And we're trying to hit 65, but we get an undershot, 47.298. So this is our YA, our first shot, 47.298. We need now, that's an undershot, so we're going to take a larger value of V now. I would maybe just try 20 for argument's sake. It doesn't matter if you get another undershot, the formula still works. So we're going to do all this again with 20, which we call VB. Okay, so off we go. So just must set up my calculations, and off we go. So M1, we have to go up to M4, or M1, I'm doing that again. Temperature 1 is the previous temperature. Now we're going back to the very start, so previous temperature in terms of X to temperature 1 is the boundary temperature 5 there, plus step size times previous slope. So we're assuming that the previous V, the initial V, is 20, hoping for an overshot, but it doesn't really matter. V1 is equal to the previous V, which is 20, plus step size 1.5 times previous slope, minus 0.02, 80 minus temperature, the initial temperature, the previous is the initial, and I get 35 here on the calculator, and 17.75. Now we go again. Temperature 2 is equal to previous temperature, 35, plus 1.5 times previous slope, 70. I suppose my concern here, if I was doing this question, is to actually bore them. You know, it's very easy to make a mistake when the work is quite boring, unfortunately. And there's no doubt in my head this kind of calculation is boring. So I think that's normal. So the first temperature is coming out 61.625. So we're almost certainly heading for an overshot here. And the V is coming out as 16.4. Temperature 3, so this is at x equal to 4.5. Previous temperature 61.625 plus step size times previous slope 16.4. Actually, this pause in calculating makes sense because some people, so this should be the previous temperature and that is back here, it's T1, but some people are kind of putting in the very previous thing they've seen, and if you actually don't calculate it, you won't make that mistake. So there's maybe some sense in this weird way I'm doing it. Anyway, V3 is equal to the previous V, which is 16.4 plus step size times derivative 80 minus previous temperature is 61.625. Let's ask the calculator now. T3 is coming out as 86.225. And the V is coming out approximately 15.849. And then finally, this is definitely going to be an overshot. Previous temperature 86.225 plus step size times previous slope. Slope temperature is V 15.849. And not worrying so much about the rounding, I'm getting 109.998, which actually rounds up to 110.00. So now I want to use my formula that I saw a little bit earlier, so I might just go and get that. So now I want to use this formula to find the correct V. So V of 0 is equal to V8. That was my first slope that I tried. I tried 10, that was shooting straight at it. Y of xf is what I'm trying to hit, which is the 65. Minus my first shot, which came out to be 47.298. Divided by YB, which is my second shot, was 110. Minus my first shot again, 47.298. And then the second slope was 20 minus 10. Bang that into the calculator. And I get 12.823. Now that is the answer to the question. It asks us to calculate, approximate t dashed of 0. This and V is t dashed. So we have done it. You can take the final shot to confirm your answer. We actually will do that. It does make sense, like, well, in the sense that if you have time in an exam, you ask yourself, have I answered the question that was asked? And does my answer make sense? And if you can check your answer, you can check your answer, and here you can. So we're going to, let's go. T1 is the previous temperature, which is the initial 5 plus 1.5 times the previous V, and that's that 12.823. And V1 is the previous, that 12.823 plus 1.5 times minus 0.02, 80 minus the previous temperature, which was the initial temperature. So this first temperature is coming out 5 significant figures, 24.235. And this one is coming out as 10.573. There you go again. T2. We're trying to get T4 to be 65 or up to rounding error anyway. Previous temperature 24. So this this is just check. It's not a part of the solution itself. 24.235 plus step size is 1.5 times slope of T, which is V, previous T, 10.573. V2 is equal to previous V, 10.573, plus step size 1.5 times slope minus 0.02, 80 minus temperature, previous temperature 24.235. Let's ask the calculator what we get. I'm getting 40.094. If you're doing this yourself, you might have small subtle differences due to how I'm rounding. I wouldn't be too worried about that. And then actually 8.9 approximately 8.9000. 5 significant figures. Temperature 3 is equal to the previous temperature 40.094 plus step size 1.5 times slope. Let's put in 8.9 now. V3 is equal to previous V, which is 8.9 plus step size 1.5 times slope of V, which is this, minus previous temperature 40.094. So this temperature 3 comes out approximately 53.444. And this one comes out 7.7029. 7.7029. And then we're trying to get very, very close to 65 now. So 53.444 plus 1.5 times 7.7029. And this comes out, we're trying to get 65. I get 64.998. So that's very, very good approximation to 65. So I'm really happy that this thing here is correct. So the work solution to this is on page 169 that we drive on. So this is a kind of a fuller question, but I guess it's saved because there's not so many internal points, because it's a rod of length 3. So we got x equal to 0, x equal to 3, and the step size of 1. And then our temperatures, we have temperature equal to 0 here. We call this temperature. So this is going to be a lot quicker than the previous question. And then the final temperature is 45. Yeah, it's going to be a lot quicker. For our initial slope, we can do whatever we want, but to me it makes sense to shoot straight at it. So you're going from at distance 0, temperature 0, that's there, to distance 3, temperature 45. And if you do a rise over a run there, or shoot straight at it, it's 45 over 3. So to me, it makes sense to try an initial slope of 15. This should be a lot quicker than the previous one with only 2 internal points. So temperature 1, the next temperature, the previous temperature is 0, plus step size of 1 here. So step size of 1 and previous V, well, we said here, it's kind of written over there. Let's write it a bit more prominently. Let's try a slope of 15. Okay, and V1 is equal to previous V, 15 plus step size of 1, and the slope, oh well, we've jumped the gun here a bit, haven't we? Because we haven't written it as 2 first orders, which is crucial. So we'll just pause for that, and we'll do it in this small space here. I guess you should have seen it above. So you would get the first derivative, call it V, goes with the initial time, which is, initial temperature, which is 0. And then if you differentiated both sides of dt dx equal to V, you'd have the second derivative of temperature equal to dV dx. So that second derivative of temperature in the question is in fact dV dx. And so you just have to do some very simple algebra to get dV dx is equal to minus 0.0140 minus temperature, with an initial value of V is unknown. We're trying this initial value of 15 by shooting straight at it, but it's almost certainly not going to work. So anyway, so what goes in here now, we can now go back. This feeds into this. The slope of V is minus 0.01. That is going to feed in here. 40 minus the previous temperature. Now the previous temperature is the initial temperature, which is 0. So this I can do in my head, and the other one with the calculation is 14.6. Now we're going to do T2. Previous temperature 15 plus step size is 1 times slope of T we just wrote down as V. So previous V is 14.6. V2 is equal to previous V, 14.6, plus step size is 1, times slope of V minus 0.01, 40 times 40 minus temperature, previous slope, so previous temperature is 15. And we're getting numbers 29.6, and we're getting numbers 14.35. And we just have to go up to T3, we're trying to hit 45, T3 is equal to previous temperature 29.6, plus step size is 1, times previous slope, previous V, 14.35, and we're coming in with an undershot very, very close to our 43.95. So we know that the answer is going to be close to 15 because this initial slope of 15, sorry, when I say the answer, the V of 0 that we're looking for. So that's the first shot. Second shot. So we'll just make V a bit bigger. We'll go with 20. So this is now my first shot. This is my YA. Let's go again. So temperature 1, V1, temperature 2, V2, and temperature 3. These are our shots. So previous temperature, again, go back, was the initial temperature of 0, on the top right there. 0 plus step size. Slope of temperature is V, previous V is 20. Here we're trying initial V of 20, so the previous 20 to V1 is 20, plus step size is 1, and the slope is minus 0.01, 40 minus temperature, and the previous temperature was 0. So we're getting 20 here, and we're getting 19.6 here. Now we go again. The previous temperature is 20, plus step size is 1, times previous slope, 19.6. Previous V is 19.6, plus step size times slope of V minus 0.01, 40 minus previous temperature. Previous temperature was 20. So this number is 39.6. And this number is 19.4. Then one more shot, 39.6, previous temperature plus step size times previous slope, 19.4. This is going to give us an overshot. We're trying to hit 45. This actually, it's 59 pretty much on the nose. And this is our second shot, YB. Now let's go off and find our formula for V of 0. It'll be on your exam paper. So here it is. We had we tried a slope of 15, shooting straight at it, and we had a bare undershot of 43.95. Then we had a second shot with a larger slope of 20, and that produced an overshot of 59. And we're trying to hit, excuse me, 45. So V of 0 is the first slope, 15, plus what we're trying to hit, which is 45, minus the first shot, 43.95. And because that was very close, this second term is going to be quite close to 0. And so the answer is going to be quite close to 15. Second shot, 59 minus 43.95. Second slope is 20 minus first slope, VA is 15. Bang this into the calculator, I am getting, I think, 15.349. Now the question, that was the previous question done, but this question here wants us to go on and approximate T of 1 and T of 2, the temperatures at T1. And like notice that T1, it does approximate temperature at x equal 1, and this approximates temperature at x equal 2. That's not usual. So for example, if we went back to the previous question, temperature 1 is approximating the temperature at 1.5, temperature 2 at 3, temperature 3 at x equal 1 at 4.5. So like these check answers that we did, in fact, this approximates the temperature at 1.5, this approximates the temperature at 3, and this approximates the temperature at 4.5. And of course, we know the final temperature that's given in the question. So this one is asking for a final shot. So let's do it. Right, so I get temperature 1. Previous temperature is the initial temperature all day long is 0, plus step size of 1, slope of 15.349. V1 is the previous V, 15.349, plus step size is 1, and the slope, I believe, is minus 0.01. The 40 minus temperature, and it'll be the previous temperature, which is the initial temperature, of 0. So this calculation is pretty easy, 15.349, and I go off to a calculator for the other one, I'm getting 19.949. 14.949. Temperature 2 is equal to the previous 15.349 plus step size is 1 times slope of temperature is V, 14.949. And actually, in terms of the question that was asked, we're pretty much finished here. Because this approximates the temperature 1 and this approximates the temperature 2. So we actually are done because we know that the next temperature is 45. Now we know that if we did everything right, so maybe we just put in a check for ourselves if we have time just to continue this on. So V2 is the previous V, which is 14.949. We just want to check our answer by seeing that we do indeed get like 45, or up to rounding error anyway. 40 minus the previous temperature. Now the previous temperature to V2 is T1, which is 15.349. And I get here approximately 14.702. And then finally temperature 3 is the previous temperature, 30.298. So step size is 1 times previous V, which is this 14.702. I'm trying to get 45, and I am actually getting that to 5 significant figures. So that's how I know that it went well. Okay.